All right, let's start the lecture for today, and we will learn more about the block cipher modes. So we have learned about the block cipher last week, and then we will learn about what kind of modes are available, and then we will also learn how we could go wrong if we incorrectly use the block cipher modes, even if the underlying the block cipher is secure. So let's start with a little bit of recap about what we have learned last week. So we learned about block cipher. So it's something like a box set here. And then you can regard this magic box. If it is provided with the secret key, then what it will do is it will transform the message M to encrypted one, the message E, but its characteristics is that like block ciphers for a secure one, we would regard that as a pseudo-random permutation. What that means is like it will generate the permutation of the numbers. So you can regard that as like some table of the numbers, one on the left side and then one on the right side, and then they're like the shuffling is completely random. And then your key will determine one of that kind of permutation. And then your numbers, if self-plied, then that will be transformed to another number based on that mapping. So you can regard the block cipher as a magic black box that transforms a message into somewhat random looking number, but that kind of mapping is determined by the key itself. So that's why I told you that you can regard the block cipher as the shuffling the card. So the determining the key for the block cipher is shuffling a new deck of the card, and then the result will be per each number you will have the corresponding the ciphertext number on it, and then that kind of the mapping would look like a completely random. And then being completely random is very important because like the older purpose of like us is like even if we send out some of the messages to public, then the adversaries will know that cannot know that that's distinguishable from the random number or not. Then that means like we could have some sort of the security. And then block cipher, even if like the data is designed for encrypting one block, we can encrypt the arbitrary number of the bytes by having a padding scheme and also chaining the block cipher again and again. So for example, suppose we have a 16-byte of data and then another 16-byte of data, then we can encrypt the first 16 bytes with the one block cipher unit, and then the next 16 bytes with the second block cipher unit, and then concatenate all the ciphertext to get the result. And then the most naive block cipher mode is so-called the ECB, electronic code book. But we practice that the ECB is quite insecure because so suppose we encrypt the 0. So for example, a white background, and then also we encrypt the sum of the black or a white and black mixed data. And then if the value is all white, then that plain text will be mapped into the specific ciphertext. So that's why even if we encrypt the data, so white part will be encrypted into the certain pattern. So that we can see that even if this is not purely white, we can see some of the patterns in the image data. So this image data is directly from the bitmap. So like so it shows that how the bit patterns look like visually. And the problem is that for the part that is not white completely, and they do have like a different part like this encrypted in a different way, but for all the whitish, pure white blocks, they will all encrypted in the single pattern. So that's the weakness of the ECB. Then that's why we need to learn more block cipher modes that's more secure than ECB, and then we will learn about one by one. So even if we have a block cipher, there could be some of the way of using the block cipher to chain it to enable like the decrypting and encrypting data for arbitrary data. And then even for the block cipher can only encrypt one block of the data, we can chain it and use it. And then how that is defined is in the block cipher mode. So we will use AES for the block cipher standard for right now, but you can think it as like we can apply the block cipher modes to any kind of the block cipher scheme. So we can apply that to DES or Camellia or some other schemes, but we will apply all these block cipher to our current standard, advanced encryption standard, AES, which is I believe the secure algorithm for now. Yeah. And then I will introduce each of the block cipher mode, ECB, CBC, and ZTR, and then how they work. And then we will also learn about how we can break each kind of the scheme if the ciphertext is allowed to be modified. So the first mode that I will introduce is the default mode called ECB. Yeah. So how it works is like that it uses block cipher encryption for the data encryption. So suppose we have a long data like a 0, 1, 0, 1, and then many other values like that. Then how will use the block cipher is like to encrypt the data, we will just use a block cipher encryption to generate the data. And then we will do that per each block. And then if the data is not aligned with the block size, then we will add the padding. Yeah, something like that. And then the decryption of the ECB is the same as like it's just the opposite of the encryption. So we use a block cipher -1, the inverse function of the block cipher, and then put the ciphertext, then we will get the plain text. That's it. So all the same key will be used for all the encryption and decryption. And then the characteristics of the ECB is that we can run encryption in parallel. What that means is that like suppose we have all the plain text available, then the encrypting of the second block is not depending on the result of the first block at all. So that means like we can run all the encryptions in parallel. So for example, if you have 4 core machines, then we can run the encryption 4 at a time at the same time. Yeah, and then we can get the encrypted data. And then the same thing applies to the decryption because it directly uses the block cipher decryption. So we can also decrypt the data in parallel. So in the decryption phase, all the ciphertexts are available at the first place, but the second or third, fourth blocks are not depending on any kind of the prior the round data. So we can run the decryption in parallel too. So ECB looks good because we can encrypt, decrypt arbitrary data, and then we can also run the encryption and decryption in parallel. But the problem is that the ECB will leak the patterns of the ciphertext based on the patterns of the plain text. So the specific problem is that suppose we encrypt the 0, then 0 will be encrypted in the fixed message at all time. And then suppose we encrypt 1, then that will be encrypted in the fixed pattern of the message. That will never be changing. So that's why this kind of the phenomena happens. So for all the white data, yeah, they will have the fixed message pattern. So it will have the same patterns for all the white background, so that we can easily distinguish the non-white the part of the bitmaps in there. Yeah. So ECB, if it is used solely, it's not secure. And then to check with the ECB is insecure, and then I prepare the three challenges for you. So this is actually one challenge, but you need to manipulate the data for 3 times to get all 3 flags. And then let me describe how each challenge would like to be. So after you understand how ECB works, so how ECB works is very simple. It directly encrypt and decrypt. And then that's why the ciphertext patterns are known. So for the known plain text, we know that what will be the 0 and what will be 1, that kind of thing. And then in the ECB attack challenge, what will be given is that you will be given by the one of the encrypted user data. So what it does is like it will create the user data structure composed like the UID, username, password, message, and admin, that kind of data. But I used a very secure key to encrypt the data as an encrypted user. But I will not give you the key, so that you cannot generate arbitrary data. But what you can do is you can manipulate with the ciphertext to match certain condition. So to play with this, you need to start with the fetch crypto. So it will not overwrite the existing the data, so that you can run it in your home directory where your crypto directory is, and it will like it will create the link for all the new challenges. And then how you can learn these challenges, like when you get to the ECB attack, the directory, then you can just run the launcher. Yeah. So I will just demonstrate that for you. So in the terminal, 1, 2, sure. Now you can see the terminal, and then so if you run fetch crypto, then it will automatically create the links for that. So when you get to the crypto directory, then you will see that the several directories, new directories that stores a new challenge. So let's go to the ECB attack, and then you can run the program with the launcher. And then this is for like protecting the flags from the reading directly. So you cannot read the flags, but while running the launcher program, then it allows our challenge program can read the flag and then be ready for you. And then, so what it asks for us is like we need to provide the encrypted file, but we have the sample encrypted file here, encrypted.user, and then we'll type that for it.
Yo, the screen is frozen.
Screen is frozen. I will share it again. Wait a second. Can you see the screen? Now it works. Great. So after typing the encrypted.user, so that's the correctly encrypted data. So the program will use the key to decrypt the data. So the decrypted user information is correct like this. And then the program will also shows that how the data is decrypted. So this is the UID part. So internally, it will be changed as an integer 1. And then username is at here. And its password is at here. And then this is the part for the message. And then is admin flag is at the end. Then what this challenge asks you is to change the UID to be 0. So right now your UID is 1, but you need to make your UID as 0. Yeah. Then you can do that by just manipulating with the ciphertext. And then before getting into the detail, let's take a look at how the entire structure looks like. So the launcher program will run the ECB decrypted.py. Yeah. And then what this ECB decrypted.py does is that, so it will load the flags, it will load the key, and then it will read the encrypted data and then decrypt it. And then load that as a user, and then print the user information, and then print the menu. So menu is this one. So either made the UID equals 0, admin as 1, no, or change the password to something else. So what the program is doing is that for the flag 1, you need to make a user's UID as 0. Then it will print out flag. And the second one, you need to make the user's isadmin flag as 1. Then it will print the flag. And then for the third one, you need to change your password, not this one, but you need to type the correct password to get it through. Yeah. So that you need to accomplish 3 tasks to get each of the flag. But I prepared a template, the py. So let me copy out of it. So I prepared some of the basic stuffs that the basic conversions that you need to suffer from. So you don't need to go through all these kind of things. So you don't need to take a look at the first part. So this is all about like converting the byte string into the string hex integer kind of thing. And then what it will do is it will read the encrypted.user file, and then it will create the blocks bytes. What that means is like that it will cut it in the 16-byte block and then store the array of these strings. So that these are blocks bytes, and then blocks hex stores the hexadecimal strings of each block. And then at the end, blocks int, it will store the integer values of each byte of the ciphertext. So you might need to play with the blocks int here, and then you don't need to take a look at this part. And then at the end of the template.py, you will see that where you should edit for getting the flag 1 and flag 2 and flag 3. And then I will describe that how you can play with this template.py, and then I will demonstrate how you can solve the challenge and then get the flag one by one. Now, let's go back to the slide. So what we will do is we want to make UID as 0 first. Yeah. But if we just type the encrypted user, then its UID is 1, and then some other values like this. Then how can we make a UID as 0? So in ECV, so the same plain text will be resulting in the same ciphertext for all time. So we know that the isadmin value is 0. That's on the last block of our ciphertext. Then what if we overwrite this block at as the first block? So that we know that the last block's plain text value is 0, right? Then just overwrite that to here. And to do that, so our block 0 stores a UID, 1 is for username, and 4, 5, 7, 6 is storing the isadmin. So what we need to do is like we want to overwrite the content of the block 0 with the content of block 6. And then how you can do that is like so in the template.py, so I prepared all the deep copied the data structures here. So you will be mostly likely who would like to play with the blocks int. So you need to modify the copied blocks int for like the blocks and then bytes. Yeah. And then copied blocks int are like the first index will choose the block number here, and then second index is the byte number inside of the block. So what we need to do is, I will describe in the code. So let's move the terminal. So for having the flag 1, what we want to do is, so blocks int would look like something like this. And then we know that UID was 1, but the is admin was 0. So that's why we want to overwrite these numbers to this part. Then it will be decrypted as 0. So what we will do is, so I just put all these numbers to the first one. Then it will be converted back to the byte string and then stored into flag 1.user. And let's see how this works. So I just run it. Then it created the flag 1.user. And then, so this is the hexadecimal output of the original one, and then my edited one. And then we see that all the other 6 rows are the same, but the first row was E979, but we overwrote that with this one, 9CVE, right? One question?
And in this case, our block size, our key size was equal to the
16 bytes. Yes. So this is exactly 16 bytes. So each row represents like each block. Yeah. And then I will run the launcher. And then now I prepare the flag on the user. And then now it is loaded, but the definition of the ECB, they don't care about where the ciphertext it is. And then we just move the valid ciphertext to the UID. So it's correct. So to get the flag, so you type 1 in here, then like it will check whether the UID is correct, then it will give you out the flag. So this is how you can solve the challenge. So any questions? Then we will do this similar thing. So we just move the isadmin 0 to here to make a UID 0, right? And then we made a UID 0, then giving the flag 1.user, and then matching that, we can get the flag. So the interesting point here is that even if we don't have the key, we can manipulate with the ciphertext and then to match certain condition to bypass some of the checking in there. So now you will feel that like the using ECB naively is not secure at all. And then we will learn how we can protect against these kind of attack too. So they don't worry much about that part. And then the next challenge is we need to make isadmin flag as 1. Now, many of you know that how we can achieve that. So can anyone answer how can we make a isadmin flag as 1? Yeah.
just do the opposite.
Right. UID is 1. So bring this and then put that in here. Yeah, that's easy. So it's the opposite. So we need to set the block 6 content from the block 0 content. Yeah. Then we need to do something like this, the opposite. Then that will show the result that, so your UID is 1, then your admin is also 1, then you can get the file. And then the third challenge. So you need to change the password to something else, but the password you should know. Then this challenge is also easy. So the password should not be the same one like this, but how can you do that is like that you can just copy the username part and then put that on the password field. Something like this, making the result of the copy of block 1 as a copy of the block 2. So copy this block into there. Then the system will regard your password as a not administrator and then type that. You can get the flag 3. So this is how you can solve the challenges. Any questions about the solving challenges part? So I believe the ECV will be easy because like it just require you to switch the rows, yeah, and then based on the plain text result, the knowledge that you have for like this plain text is 0, this is 1, something like that, and then you can arrange the ciphertext at your wish, and then you can do whatever you want. Yeah. So the weakness of the ECV is that there is a fixed plain text to ciphertext mapping, so we can easily manipulate with that. So that's a serious problem. But everybody knew this kind of problem exists, so that they try to come up with the methods to avoid that. And then that method is so-called the CBC, Cipher blockchain mode. So please note that the Cipher blockchain mode exists because there was a problem that the plain text to ciphertext mapping is leaking in ECV. So how they designed the CBC, the new mode, is that, so there must be one random number at the start. So the another requirement on top of the ECV is that when we apply CBC, we need to get a random number, and then that random number is called as an IV, initialization vector. So you can see the random number right here. And then how we will use this random number is that to the first block of the plain text, we will apply XOR, the plain text, and the IV. So IV is completely random. So get the first block. We will XOR the first block with the IV. So the content, the result will be look like completely random. And then we will encrypt that. And then the reason why it is called the Cipher blockchain, so the ciphertext of the first block will be supplied to the next block XOR value. And then the reason why we are doing this thing is that the IV is randomly drawn. So IV XOR plain text 0 will be look like completely random. And then suppose we are using a good pseudo-random permutation block cipher, then result of the encryption will be looking like completely random too. So we can regard this as a new random number. And then if we apply XOR with this new random number to the plain text, attacker don't know what kind of things will be coming out from the plain text. And then we can reuse this random to mix it to the next level, next block plain text. So the entire result will become somewhat random, and that will be encrypted again and again. Yeah. So the sequence is that IV will be XORed to the plain text block first one, and then encrypt. And then the result will be XORed to the plain text of the next block, encrypted, XORed to the plain text of the next block, encrypted again and again. And then how can we do the decryption? So the decryption is the opposite of all the operation. So we apply XOR first and then decrypt, encrypt. In that case, we need to decrypt the ciphertext first and then XOR IV for the first block. And then for the second block, we need to decrypt the second block first, and then XOR the first ciphertext block to get the plain text of the second block. So that we need to chain these decrypt XOR again and again. Yeah. So the benefits of the CBC is that, so one of the weaknesses of the ECB was like 0 was encrypted into the fixed value, 1 was encrypted into the fixed value, so we can switch the ciphertext and then reuse it. Yeah. So that was the biggest problem. So let's make the each input to the block cipher looks completely random. Yeah. And then how can you make the each input to be random? And that's easy. We can, if we mix some of the random looking number to the plain text, then we can achieve that. So the solution is we will just draw one random number, then mix that with the first plain text. So this will be completely random and goes into the cipher. And then resulting ciphertext looks like random, that will be mixed into the next plain text, then again and again. So we will keep that all the input to the block cipher will be completely looking random. So by doing so, we can hide the ciphertext pattern, not leaking from the plain text pattern is not leaking in the ciphertext pattern. So by doing this, the same result of the ECB encrypted, CBC encrypted look like this. So that you can see that from the CBC encrypted, it looks totally random because there's no certain patterns exist for the ciphertext to plain text and mapping each other. Yeah, because we will add the random number at any time of the block cipher running. Yeah. So this is the result of the CBC. So the CBC definitely looks more secure than ECV in terms of like we cannot switch the location of the valid ciphertext to get it something correctly, or also like the getting the pattern of the ciphertext out of it. Yeah. But the CBC has a little bit of drawback. So we cannot parallelize the encryption. So let's take a look at the encryption phase. So we have an IV, then for the first plain text block, we can encrypt without any kind of restriction. But when we need to encrypt the second block need to be XORed with the ciphertext of the previous block. So the previous encryption need to be finished to start the next encryption of the block cipher. So that prohibits like the parallelly running the encryption of the CBC mode. So the CBC mode must be running in serial, so it cannot be parallelized with the multi-core. Yeah. That's the one of the drawback. But for the decryption, we can run in parallel because what we need is IV and then all the ciphertext. And then when we get to the decryption phase, we all have the old pair of the ciphertext. So we can, so when we decrypt the third block, then what we need is like a second block of the ciphertext and then third block of the plain text. And then third block of the ciphertext. We all have those, so that we can run the decryption in parallel. So make sure to know that there is an asymmetry between the encryption and decryption. So for CBC, we cannot parallelize the encryption because we need to get the encryption result of the previous block to correctly encrypt the current block. But in decryption, we all have like the older encrypted block. So for the ciphertext, and then we only need to decrypt a certain block, we only need that block and then previous ciphertext block, but that's already computed. So that doesn't restrict parallelizing the decryption. Any questions up to this point? Then let's move. So let's move on to the CBC attack then. So we learned about CBC and how it works. And then the important thing is like the certain blocks will be XORed to the plain text. Yeah. And then we have the same setting in the CBC attack directory. And then we have this kind of the encrypted data, but we need to make the similar thing. We need to make the UID to be 0. We need to make the isadmin as a non-zero. Yeah. And then we need to change a message specifically from boring to superb. Yeah, that's your task. And then let's go through like how we can do that. So to make a UID 0, so you want to replace this one. But previously, we just copy all the blocks from here to there, but that only works for ECV. For CBC, it will never work. Because even if we switch the row, then it will be decrypting in a totally different number. Yeah. So I will show you how we can attack the UI, we can change the UID. So this is the CBC decryption logic. And then you can regard that these colored boxes are ciphertext of this plain text. And then these purple ones are the real plain text. And then we have a UID encoded as 1. And then how it will be decrypted is that it will be decrypted by the block cipher first, and then we will apply XOR with the IV to get the real plain text. So this block will be decrypted as 0000001. And then we want to change the last one to be 0. And in CBC attack, to change the corresponding plain text, we don't manipulate this ciphertext. We need to manipulate this value, the value that will be XORed into this plain text. So because we know that plain text value will be 0000001, yeah. Then what if we apply XOR into the IV? So what that means is that like if we change this to 1, then this 1 will be changing as a 0. So CBC, they protected the ciphertext itself. That's very good. But the problem is that they use the simple XOR to the plain text. So if we want to edit one of the block, then we can edit the block before. For example, the XORed value, the value will be XORed to the plain text. So for this case, we can manipulate IV. But for this block, if we want to manipulate the plain text and these characters, then we need to manipulate this ciphertext, because this ciphertext will be directly XORed to here. So to change the UID, so we need to manipulate the first blocks, the not last byte. So the reason is, so with the CBC mode, the first block will contain the IV. And then to manipulate the last digit of the UID, then we need to manipulate the last digit of the IV. Yeah. So that's how you can manipulate the data. Yeah. And then by doing so, you can see that your UID will be changing as a 0. Yeah. And then let me demonstrate that in the terminal. So this is the terminal. Then I will move to the CBC attack. And then if we run the launcher, so this is the same data structure. So it has a UID 1 and then this kind of data, and then encrypted with the CBC mode. And then I will go to writing some of the solutions here. So let me first try the previous method, just overriding the isAdmin to the UID part. So right now, each blocks will be composed as starting from IB, UID, and then isAdmin. So I will just copy these things for the reference. Then put it here. And then for the prior method to attack the ECB, how we did is copy the blocks and then int 7 to be blocks int 1. So this actually putting the isAdmin part into UID part. So the offset is a 1 off than the ECB because ECB has no IV. So the first block, so in CBC mode, the first block that will be sent is always the IB. Yeah. So that's why if we shift to offset by 1. So this actually overrides all the blocks for the UID to be all the blocks for the isAdmin. And then we will see how it will be decrypted. So I run it and then run the launcher, then flag one.user. Then it says invalid literal for int. So it tries to convert some of the string to the integer for UID, and then that was decrypted in weirdly, yeah, because we just move the ciphertext for the isAdmin to the different position, but in the CBC mode, it will be decrypted in completely random, so that we cannot use that kind of the moving around, moving the ciphertext rows to get it decrypted correctly. Yeah, so that method does not work. But in this case, how we can do is we can play with the IV, but what we want to do is, so we want to change this 15, 0, and 1 to 15, 0, and 0, right? So we want to make the last one as a 0. So how we can do that is we can make the IV to have a flipped bit for the last byte. So the 0 row, 0th below row, we have an IB, and then for the last byte, we will just flip the last bit. So XOR with the 1 means that flipping the last bit. Yeah, one question. So suppose the ID byte was 0. If you said a 0, you didn't change anything. So XOR with 1 means that if it was 0, then it will become 1. If it is a 1, it will become 0. So that's why I'm flipping the last byte. Yeah. And then the XOR is so if we apply XOR to this number and then do that again, then that will have the same effect. So what we want to do is we want to apply the XOR to the last byte to here. So if we cannot apply that to the plain text, then we can also apply the same operation to the number that will be XOR'd to that plain text. So that's actually the same thing. So we will do this, and then I will run it, launcher, and then flag one.user. Then you will see that now the UID becomes 0. So that we manipulated the IB and then apply XOR to that, and then that is directly shown as an XOR, applying XOR to the plain text. So you can get the flag by manipulating the IB. So this kind of code can change the last bytes, and then we can bypass the check, and then making the UID as a 0. Then what about the making the isAdmin as 1 or other value? So we know that the isAdmin variable is at the end of the block. Yes. And then we need to change this 0 to 1. Yeah. And then to do that, to change this value, we need to manipulate not this one, because this block will be XORed into the plain text of the last block. So we will flip the last bit of this one, then it will flip at here. That's how the attacks for CBC works. So what we will do is to make a zmin as 1 like this. We will flip the last byte, and then let's try to do that. So for the flag 2, so we have a block 7 is admin. So we will alter the block 6, and then for their last byte, we will flip the bit. Then let's see what's happening in the launcher. So I will put the flag to the user that I just created. Then let's take a look at this. So isAdmin flag became 1. But can you see that the previous block got screwed up like this? Yeah. The reason is, so actually now the isAdmin is non-zero, so we can get the flag. But the important thing is like the why this block is decrypted weirdly like this. So only for this block. And then let's take a look at how the encryption decryption works. So take a look at here. Then we manipulate this block to change the result of this block. Then we didn't manipulate this ciphertext. So it'll be decrypted correctly and then XORed correctly. So, and with the manipulated value, so we can control this bit. But the problem is that the precondition that the prerequisite that we can manipulate this bit is like we need to manipulate this ciphertext. But when we manipulate this ciphertext, we cannot control how it will be decrypted in here without knowing the key. So those bits we cannot control. So the important thing here is that in CBC, so in ECB, by changing the row, we can perfectly generating the correctly decrypted content. But in CBC, what we can do is we can manipulate some of the bits by applying XOR to the XOR material for that plain text, but that includes the playing with the ciphertext. But if we play with that ciphertext, we cannot ensure that what that message will be decrypted to. But in this challenge, we don't care about that. What we care is about the value of the isAdmin. So I didn't create this challenge to make it the challenge as easier, but in reality, this is actually happening. So there are some of the data field that you don't care about the data value itself, but while there are some kind of the data field like that, there is some of the data field that we need to take care of. For example, something like a value isAdmin. Yeah. So by doing this kind of trick, so although you will screw up these kind of the blocks value like that, but you can at least control some of the variables for that. Any questions to this approach? So even if you screw up some of the previous blocks, then, but if that is not interpreted by the program, then you can ignore that. So the third challenge is that you need to change this the boring into the word superb. Yeah. And then now some of you get it to like how you can do it. So to do that, so there is a plain text block, boring class. You need to change this boring into superb, right? And to do that, to change the value of this ciphertext, you need to apply XOR to this ciphertext, right? And then how can you do that is, so even if the data is encrypted, each byte will be perfectly aligned. So byte 0, XOR value will be XOR to the byte 0 of the plain text. So you can get the exact position. So there's a white space, a white space. So this is actually the third position. So the third position, from the third position to the 9th position, you need to apply XOR to this value from boring to superb. So that I marked it as a red 370 space CR. So if you apply the XOR result of the boring and superb onto these characters, then your character will be changing from boring to superb here. So how can you do that? It's like I will briefly show you on the code in here, but I will also demonstrate that in the terminal. So we first need to get the key, XOR key, for like how we can change boring to superb. And to do that, I prepared the 2 string, boring and superb. These are all size 6. And then going over each character, I will get the integer value of the string boring, and then integer value from the string superb, and then XOR them, and then store that as a key. And then for each key, I will apply each key XOR to the ciphertext block of this one. Yeah. And then from the index 3, because the character B or R starts like a space, A space, yeah, it starts from the index 3. And then the result will be, so you can change the boring to superb, but you should screw up the block prior to that, yeah, because you need to play with the ciphertext. So I will demonstrate how you can manipulate the XOR values for the changing the boring to superb. So that's the flag 3. And then I prepared a 16-byte aligned string here. So this is the first block, second block, and the third block. And then in the third block, you need to change this BORAING to superb. And then to do that, let's get the XOR key first. So we can prepare a string boring, and then string superb. Then we can prepare the key array. And then so from 0 to 5, and then what we will do is key will store the integer value of each character on string boring, and then integer value of each character of the string superb. And then key will store that. And what we will do afterwards is that, so message block 6 will contain the superb, somewhere here is these 6 characters will be decrypted as a boring. Yeah, I don't know what these 6 characters in encrypted format. Yeah, but to alter these characters, we need to play with the block, the previous blocks, the same position, and then apply the appropriate XOR values to that. Yeah, so we need to play with the block 5. And then what I will do is for block 5, and then our index is 0, 1, 2, 3. So start of the keyword B is 3. And then we will apply the XOR key in there. And then to do that, for each key, so we will change the XOR value. So change the ciphertext and then apply XOR to change boring to superb. So I will run the solution, the Pi, and then run the run launcher, and then like 3.user. Then can you see that even if I screwed up on the previous blocks of this encrypted one, then the keyword boring was changed to the superb. That's how you can apply XOR to the previous ciphertext block to get control over the plain text. So after that, if you type 3, then you can get the flag out of it. So any questions about this challenge? So it's all about applying XOR, and then you need to figure out where you need to put the XOR value on it. Yeah. And so how we can do that is like we can apply XOR to here, then we will screw up for this block, but we can take control of the plain text here. So this is how you can do that. And then this is the result. So let me summarize the ECV and CBC. So good thing about the ECV is that we can do encryption and decryption in parallel. It's so fast. That's good. But the problem is that the attackers can easily stitch ciphertext to build a valid plain text. That's problematic. And then it also leaks the ciphertext, plain text patterns in the ciphertext. That's why we can read the characters even for the encrypted image. So that's not good. But to counter that, CBC has come into, and then the good thing is that the CBC we can decrypt in parallel. But because the encryption of the next block is depending on the encryption result of the previous block, we cannot run encryption in parallel. Yeah. But another good thing is like it does not have like a fixed pattern in the plaintext and ciphertext pair. So directly switching the ciphertext blocks will not work for the valid decryption. But the problem is that still there's a way to manipulate the plaintext by screwing up some of the ciphertext, because that will be XOR'd directly to the plaintext. Then if there's any other mode, then we can use the decryption and encryption in parallel. And also the ciphertext pattern is not fixed, then that's much better than CBC, because in CBC, we cannot encrypt in parallel. Yeah. So some cryptographers came up with the counter mode. Yeah. And then what the counter mode is that it's like it is a little different. So it does not use encryption, decryption for encrypting the data. In contrast, how do they use encryption is encrypting the counter to generate the random number. And then, so what that means is that like they do not encrypt the plain text, and then they will encrypt the counter and then the resulting ciphertext will be XORed to the plain text. And how that works is that, so to use the counter mode, we need to set the random nonce. So in CBC mode, we need to get an IV, initialization vector, as a random number. But in counter mode, we need to set a random nonce. And then how we will use this nonce is that, like, the after this nonce, and we will attach the counter number 1. And for the first block, we will encrypt this number to get some of the random-ish number like this. And then for the second block, we will encrypt the nonce attached with counter 2. Third block, nonce with the attached with the counter 3. Nonce, counter 4. So the encrypted value with this block cipher does not contain any of plain text. But if we use a pseudo-random permutation for the underlying block cipher, these numbers would look completely random. So we use this block cipher as a random number generator. Yeah. So do you recall the example that if we can have a honey jar that spit out all the random numbers, yeah, then we can share that and then use the perfectly secure encryption scheme, the XOR. So this is on the same path with that. So we can use the block cipher in the counter mode and then use that as a random number generator for the both side. And then we just apply XOR with the plain text to get the real ciphertext. So the encryption looks like encrypting the numbers and then apply XOR. And then the decryption logic is exactly the same. So previously, we need to use the decryption logic as an inverse function of the block cipher. But here, we don't need the inverse function at all. What we need to do is just encrypt the nonce and the counter, and then get the result. And then apply that XOR to the ciphertext. Then we can get the plain text result. So the important point here is that we don't use a decryption function at all. And then encryption and decryption, these logic are exactly same, but the only difference is that in encryption, we apply XOR to plain text. In decryption, we apply XOR to ciphertext. That's the only different part. Then the benefits of the CTR counter mode is that we can encrypt in parallel, we can decrypt in parallel, because there's no dependency at all. Yeah. But what will be the weakness in CTR mode? Can anyone point? Yes.
Does the loop counter always start at 0 or 1?
Pardon?
Does the loop counter that like you multiply by, does it always start at the same number? Because you could just.
So it does not have to be a same number, but the same number to be decrypted correctly. So like how we use the counter mode is like suppose you and I wants to use the counter mode, then I just draw the random number and then let you know about that random number. And then starting from there, then we will add 1, 2, 3, 4. And then because like it was chosen by random at the first place, so there's a chance that attacker would observe the same number very low. So that's how we make the security out of it. And then we learned about how we can attack CBC. So even if we don't know which ciphertext will be decrypted into which plain text, because the CBC uses XOR. So previous ciphertext will be XORed into the current ciphertext. So we need to manipulate the previous blocks of ciphertext to manipulate the plain text in CBC. But what about CTR? Yes? Yes. So that's exactly true. So attacking the counter mode is much easier. So suppose you want to change this value 0 to 1, then you need to apply the XOR and hit the ciphertext. So change the 1 as a 0, then it will result in 1. Yeah. So that you don't need to go like a 1 block before. So the directly manipulating the ciphertext will be result in the direct manipulation in the plain text. So I will demonstrate that variability with the terminal. So in CTR mode, although it gives a little bit of benefits for the attackers, it will give the full freedom for the attack. And then I will show how it goes. So there's a same set of the program with the CTR attack. So with the encrypted that user, so the same prepared attacks, but what it says is that like you need to make the UID to a specific number for now. Yeah, not for one. You need to make it as a 1, 2, 3, 4, 5. Yeah, and then I will demonstrate how you can do that. Yeah. So we copy the template.py to the solution.py, and then I will work for the create file for flag 1. And this one will generate a flag1.user. Then I will transform the UID from 0001 to 12345. Yeah. Then to apply the XOR, I will get the XOR key first. So I will do the same thing. So I will prepare the XOR of the each character of the 00001 and then 12345. And then, so these blocks will come from the nonce first. So the UID will be on the first block. So index 1, and then for the index 1. So for the blocks in the index 1, that's the block for the UID. And then we will apply the XOR for the last 5 digits of it. So how we can do that is, so we want to XOR. So if I is 0, then we want to XOR the value to the last one minus 5, 4, 3, 2, 1, so that we can apply it like this. And then let's try to run it. So for this case, I directly modify the ciphertext block itself. Then it will show on the bit flip on the ciphertext will directly show on the bit flip in the plain text. So then I will run it within the launcher. So I type the flag1.user, and then that value is changed to the 1, 2, 3, 4, 5. And then the second challenge is like you need to make the this one as a 31337. So you can easily do that. So exactly the same thing. And then for the third one, so for in the CTR mode, you don't need to screw up the blocks previous to the yours plain text. So you can accurately apply XOR to switch this warring to super. Yeah. Then you can solve the third challenge. And then I believe the CTR mode is much easier than CBC, but for the historical purpose, I described in the lecture from ECV, CBC to CTR. Yeah. Yeah. So the weaknesses about the CTR mode, counter mode, is that it's good, but the problem is like the bit flip in the ciphertext will be directly shown in the bit flip in the plain text. So it's much more easier to manipulate. And then, so you guys may think it weirdly, like even if we use the AES, the believed to be secure cipher scheme, and then the ECB, CBC, CTR, these are all archived standard block cipher mode. But I demonstrate that there are ways that like this kind of the encryption can go wrong. But do not get it weirdly. So our encryption scheme is secure. So, but the reason why we have that kind of weakness is that the way of using crypto is quite incorrect for now. So to correctly use the cryptography, you shouldn't let the attackers play with the ciphertext. So there are two types of the attack. Theoretically, is so-called chosen plain text attack and then chosen ciphertext attack. And then most of the schemes itself are secure against chosen plain text attack. And then so I don't want to go detail about the chosen plain text attack. Theoretical meaning is a little different, but the implication of it is like so if the sum of the scheme is not secure against chosen plain text attack, that means there's something that attackers can do by manipulating the plain text. So most of the block cipher schemes are like the secure against chosen plain text attack. So we will not cover that thing in here, but the block cipher scheme itself is not secure against the chosen ciphertext attack. What that means is that like if the attackers can play with the ciphertext, then there's something that attackers can do. Yeah. So I'm attacking that part. So that's why like those examples are exhibiting the weaknesses against that. So by exploiting that kind of weaknesses, you will learn more detail about like how each block cipher schemes work. And then later in the next lecture, what we will learn is like how we can protect the integrity of the data. So we will combine the block cipher encryption and then cryptographic hash to make the ciphertext cannot be modified, and then we can detect if the ciphertext is modified or not. Yeah, and then with that mechanism, we can make the entire cryptography use as a secure. So right now, all the schemes are not secure against chosen ciphertext attack, but the schemes that we will learn next lecture that will involve the secure scheme against the chosen ciphertext attack. So not susceptible to like all these attacks. So the challenges that I prepared are all about like this block cipher mode. So ECB attack is the one like the example. So if you like switch the rows, then like you can make the certain ciphertext decrypted correctly in different location. So you can change the UID, is-admin, or password accordingly. And for the CBC, to attack that, what you can control is like the previous value. So either IB or the previous encrypted block that will be directly XORed to your plain text. So any kind of bit flip in that block will show in directly on the plain text. And then for the CTR, so any bit flip to the ciphertext will be shown directly on the plain text. So the attacking CTR will be much easier than CBC. So how I recommend is like try to solve the ECB attack first, and then solve the CTR attack next. And then at the last moment, try to solve all the CBC. Yeah. And then there's one more challenge called the CBC is secure. Yeah. And then this challenge I put there, I put it there for like teaching you about like what is the power of the brute force attack. So what it entails is that so there's a challenge called the CBC decrypt. And then when you get to there, then so it has an encrypted flag file. And then this encrypted flag file is indeed encrypted. securely. And then how it is encrypted is with this Python script. And then what it does is that it gets the it gets the 16-byte key, and then with the 16-byte random IV, and then open the flag, and then encrypt it. So like encrypted flag contains the encrypted data, yeah. And then we don't know the key, but the key was selected from like the one of the password in this corpus of the password. So that you can take a look at the password list of txt, and then your task is try to decrypt the flag and get the flag by using the one of the password in the list. So I prepared the template.py as like you will have the list of the passwords. And then what you need to do is like go over these kind of the list of the password, set the key, but you need to write how you can create the AES CBC cipher. You can refer to the encryption Python script, and then how you can decrypt it. And then from the decrypted text, so the correctly decrypted text starts with the CS370 braces as a flag. So like you can verify that if you found like a correct password from the password list and then decrypt the flag. So this challenge is asking you to launch the brute force attack. Try like all the password listed in here, yeah, and then decrypt the flag and then submit it. So any questions to the challenges? So it's all about there is a correctly decrypted file, and then you need to manipulate with the ciphertext to bypass some of the checks and then getting the flag. So in summary, we learned about the 3 different mode of the block cipher, and then one is ECB. So how we use ECB is like it directly use a block cipher as an encryption and decryption, yeah, and do nothing. But the good thing is like we can run encryption decryption in parallel. But the problematic thing was like it leaks the ciphertext plaintext pair pattern. And for CBC, to kill that kind of pattern leaking, we want to blend any kind of random number to the plaintext for all time. And to do that, we need to prepare a random IV, yeah, to be XOR'd to the plaintext first. So the first block is like the encrypted and random, but the result of the first encryption will generate somewhat random number, and then we can use that number to be XOR'd to the second plaintext. So we can make sure that your plaintext will be XOR'd with the somewhat random number, so we can kill the pattern leaking in the ciphertext. But the problem of that approach is that like we can run encryption, we cannot run encryption in parallel. We can run decryption in parallel, but for the encryption, we need to wait until the first block encryption finishes to encrypt the second block, because that value need to be XOR'd. And then another weakness is that like to control over the plaintext, we need to manipulate the ciphertext of the block right ahead of that, and then applying the XOR on it will be directly shown on the plaintext of the decryption. And for the CTR mode, so we can run encryption, decryption parallelly, and also like the ciphertext to the plaintext pattern will not be leaked because we will not reuse the random nonce and counter at all. Yeah. But the problem of that approach is that like it will just using block cipher as a random number generator, and then it will just apply XOR. So any XOR applied to the ciphertext will be directly shown on the plaintext. So this is the summary. And then let me check the question on the, yeah, right. Yeah, this is the summary, and then so please, so the lecture is finished at here, so that you may leave if you don't need some of the recitation time. But I will stay here, so please stay here for the like if you want to get help for solving challenges. Yeah, please stay here, and then please ask any questions while solving the challenges.